Hello, Morris. Is that a pacemaker you have? Oh, I see you're chilling by the wall. Uh-oh, what's happening? Morris, is that an RFID reader? Uh-oh.
The purpose of our project is to develop a system that is capable of detecting electromagnetic interference in pacemakers from RFID devices. We want our system to be universal and able to gather a broad range of data, so we want it to be usable in both hospitals and public places. Unlike most design groups, our target audience is not going to be directed toward the general public. It will be more prone towards pacemaker manufacturers, RFID designers, and hospitals. In the United States, each year there are about 740,000 cardiac devices implanted each year. So it is important for these devices to work both properly and efficiently. So we want to investigate the potential hazard of low-frequency RF devices on pacemakers, and the main focus is going to be the ping rate that these devices produce. Here we have the EKG from a heart shown in the upper portion. In the lower portion we have the ping rate. As you can see, the ping rate is going to have a short burst and then a low, and then another short burst and then a low. And this is a problem with demand type pacemakers, and all that means is that the pacemaker is going to be active when it senses no heartbeat, and it will shut off when it senses a heartbeat. So in the worst case scenario, the pacemaker sees that ping rate, interprets it as a heartbeat, and then shuts off.
In order to simulate the environment of the chest cavity the pacemaker is located in, we are using a plastic container. Inside the container there is a saline solution used to mimic the electrical characteristics of the human body. Once the pacemaker is inside of the container, we will then need to correctly read in the pace signal from our microcontroller so we can pinpoint the exact time for EMI. To find these EMIs, we will be conducting tests around various RFID emitters around hospitals, and also buildings such as the Koblasz building. Once we have conducted the test, we will gather the information and see if the pacemaker was affected by the emitters. The following slides detail the design challenges we've come across. One of our challenges was to understand the various electromagnetic compatibility testing protocols. These ensure that proper techniques are used on the device when testing for possible interference. Another challenge was choosing the correct ping rate the RFID would pace to create the most EMI. At high rates, there will be minimal interference due to the pacemaker's low-pass filtering. The pacemaker, however, can't block the lower ping rates produced by the RFID emitter because it's these frequencies that tell the pacemaker if pacing is necessary. And we are interested in the lower ping rates from 0.5 Hz to 2 Hz.
We encountered other design challenges when making the container. When constructing the container, we needed to keep these four design parameters in mind. The first was portability. Our container needed to be portable because we'd be taking our pacemaker to different RFID setups around hospitals. The second design parameter was leak-proof. It needed to be leak-proof because our container would be full of saline solution. Our third parameter was that our pacemaker lead needed to make a loop. Our pacemaker lead needed to make a loop because it would need to mimic the worst case scenario for RFID interference. So when we test it to different RFID readers, we'd have a better chance of interrupting the pacemaker. And last, the pacemaker needs to be stationary while inside the container so we can get consistent results. Here's a picture of our final setup. The container is to the left in the plastic box. Inside is the pacemaker. Jutting from the container is the sensing lead. The sensing lead is hooked up to the sensing apparatus on the right. Inside the sensing apparatus is the Arduino microcontroller and outputs the sensing information through LEDs and buzzing noises. Here is a picture of the pacemaker inside the container and the rig that holds it. As you can see, the pacemaker is tied with zip ties to a blue 3D printed plastic board. This board itself is glued to the side of the container, and the entire setup is suspended inside a saline solution.
Here's our sensing apparatus that hooks up to the pacemaker. From left to right, you can see a reset button, 3 LEDs, an on-off switch, and a potentiometer. Before I go into software, the red LED represents if the pacemaker is not pulsing, yellow represents a pulsing, which it is in time with, and the green is the output of our comparator. Here's a flowchart for our software that is on the Arduino. For the Arduino, there's a interrupt that when the pacemaker pulses, it will set P equals 1 inside the software. And if P equals 1, then it will turn on the yellow LED and beep the buzzer. If 2 seconds have passed, or whatever period that the pacemaker has, then the red LED will turn on and the buzzer will turn on continuously till another pulse is sensed. A hardware schematic of what is connected to the Arduino. As you can see, we have a op-amp and a comparator. The op-amp was our previous design, which you can use as a comparator with no feedback, but it turned out it didn't work that well. So we ended up getting a comparator. The voltage source you see is from the pacemaker, and the output of that comparator is input into a Arduino pin which controls the interrupt. Here's a simulation of the comparator and the pacemaker. The purple represents the pacemaker, and you can see a tiny 30 millivolt pulse. And as that pulse happens, you can see the green line, which is the output of the comparator, that goes high and causes the interrupt within the code.
Alright, so for sensing the signal, just to reiterate, we use the Arduino Pro Mini to sense the pacemaker output with the comparator and comparator circuit. The Arduino has an LED and sound functionality, which includes the yellow and red light that you'll see later on in the video at the end, and a beeping noise. This implementation is for live testing, where you can see on the spot whether or not the pacemaker is pacing or whether the pacing has been inhibited. Here is an oscilloscope capture showing the pacemaker output. You can see here the signal amplitude was approximately 30 millivolts. The period of the signal was about once every 2 seconds, which was confirmed with the Dr. Michael Lloyd from Emory. And here is just a model view of what our design is. You have the torso simulator with the output leads being inputted into our Arduino, and those inputs are used in the comparator in order to turn on or off the LEDs and the beeping sounds.
So the first issue we ran into with our project was the MSP430 microcontroller was not fast enough to sample the pacemaker signal. So a solution to this was to switch to an Arduino, which had a faster processor, and it's a little bit easier to program. Second problem we had was that the sensing equipment was not shielded against electromagnetic interference. So to prevent interference, we shielded all the wires that led to the sensing equipment in Arduino. Our preliminary testing was done at the Koblasz building. We used various RFID readers and scanners, and our testing showed some level of interference depending on the type of RFID reader we used. To confirm our results, we will continue testing at Emory University Hospital. On the next slide, we show a video of the demo that we used demo of testing that we used in the Koblasz building.
Pacemaker box in a neutral position away from the RF reader, and it's working as expected. As we move our box closer to the reader itself, it should show interference and shut off the pacemaker. And it does that, as expected. When we remove it from the RF reader slowly, the pacemaker should resume its pacing.
So for our cost, we had three major components. The Arduino, which consisted of all of our electrical components, including resistors, capacitors, potentiometers, as well as the Arduino itself. This signal detector cost about $31 market price. For us, it was about $5 due to most of the parts being lended to us from the senior design lab. The plastic containers were $1 each, and we used 3 containers at a total of $3. And to seal the container and make it waterproof, we used epoxy and sealant, and that cost about $15. So that brings our total market cost to about $49.96, while our total cost was about $23. In the future, we plan on testing a greater range of pacemakers and ICDs, and we also want to combine the sensing electronics with the chest simulation container to build a more compact testing rig. We also want to add a memory component to the microcontroller and Arduino to record sensing data, so we can go back and look at when the pacemaker actually interferes with RFID. Questions, comments, or suggestions?